At the outer edge of our solar system lies Pluto, a celestial mystery that fascinates astronomers and space enthusiasts alike. Pluto's reclassification as a dwarf planet, once the ninth planet in the solar system, did not diminish its appearance. However, new information has emerged in the astronomical community. There are whispers of a possible conflict between Pluto and its neighbor Neptune. What does this mean for the future of our solar system? Are we on the brink of an unprecedented global collapse? Pluto's history is one of mystery and speculation. Since its discovery in 1930, Pluto has fascinated scientists with its unusual orbit, unlike the main planets in our solar system. Unlike the circular orbits of other planets, Pluto travels very slowly around the Sun, taking 248 years to travel out of the solar system. The eccentricity of Pluto's orbit, which is 17.1 degrees to the orbital plane, adds to this puzzle. But what really sets Pluto apart is its conjunction with Neptune's orbit, a conjunction that occurs about 20 years per orbit. The tug-of-war between Pluto and Neptune has long fascinated astronomers. Despite the near miss, there was no accident. But why? The answer lies in the complex dance of gravitational forces that govern their orbits. The orbital position ensures that Pluto crosses the path of Neptune, which is more than 90 degrees from Neptune. This shield prevents the two heavenly bodies from approaching. But can this simple balance be a distraction? Could one day we see a dangerous collision between Pluto and Neptune? To understand how powerful it is, we need to look at the power of the three-body problem, a challenge that has puzzled scientists for centuries. The three-body problem involves predicting the motion of three celestial bodies such as Pluto, Neptune, and the Sun based on their interactions. In the case of Pluto and Neptune, this problem is exacerbated by the presence of other large planets in the solar system, such as Jupiter and Saturn, which have a strong planetary influence. Astronomers have identified several key factors that contribute to Pluto's stability. Circuit. As mentioned earlier, orbital expansion plays an important role in keeping Pluto and Neptune at a safe distance from each other. In addition, the spring and fall in the orbit of Pluto will be much higher than the orbital plane of Neptune when the two bodies are close together. This extra layer of protection reduces the risk of a crash. But despite these stabilizing forces, Pluto's orbit is unstable. Numerical simulations performed in the late 1980s show that even small changes in Pluto's position and speed can cause large changes in its orbit within 1,000 years. This chaotic behavior is a reminder of the delicate balance that exists in our solar system, one that can be disturbed under the right conditions. The influence of the giant planets in the solar system cannot be overestimated. Jupiter, with its massive mass, has a powerful influence on all the planets in the universe, including Pluto. Saturn, despite its smaller size, plays an important role in shaping the life of nearby celestial bodies. These two giants work together to stabilize Pluto's orbit, ensuring that it remains in a very stable orbit for billions of years. However, Neptune has a special relationship with Pluto. The two bodies are in 3:2 harmony, meaning that Pluto completes an orbit every third of Neptune's revolution around the Sun. This sound helps to maintain Pluto's orbit and prevent it from touching Neptune. But what if this delicate balance is disturbed? Could the impact of another object, such as a passing asteroid or comet, change Pluto's orbit and put it on a collision course with Neptune? Despite its stability, Pluto's orbit remains a source of intrigue and concern for astronomers. The concept of periodic chaos, where small changes in the position or speed of a celestial body lead to large changes over time, is especially true for Pluto. Even a small change in Pluto's position or speed can have a big impact on its long course. By making small changes to the starting conditions for these simulations, astronomers have learned how small changes can produce different results. The surprise highlights the challenges of predicting Pluto's future path and raises questions about the long-term stability of its orbit. The collision between Pluto and Neptune has the astronomical community very concerned. Prominent astrophysicists such as Neil deGrasse Tyson and Michio Kaku expressed concern about the results of that event. Tyson, who helped reclassify Pluto as a dwarf planet, has warned that the three-body problem is too serious, saying the Pluto-Neptune collision could take a long time. But what was the result of that meeting? For Pluto, this match is bad. Due to its small size and icy structure, Pluto was destroyed by impact, scattering debris throughout the solar system. This debris could threaten other planets and moons, and could threaten the stability of the entire solar system. Neptune, though larger, did not die. This collision could change Neptune's atmosphere and have significant consequences for the dynamics of the planet's atmosphere. Disrupting the balance of the solar system raises troubling questions about the long-term stability of our planetary system. Leading theoretical physicist Michio Kaku has a unique perspective on the potential collision between Pluto and Neptune. Kaku's work in string theory and his understanding of the relationship between celestial mechanics and theoretical physics provide a deeper understanding of the forces at play. Kaku sees the study of Pluto's orbit as a window into the future. By understanding the planetary interactions and orbital dynamics of celestial bodies like Pluto, we can gain valuable knowledge to help guide the universe and beyond. This knowledge can help us predict possible disasters and plan missions to the outer regions of the solar system. Kaku also emphasizes the connection between celestial mechanics and fundamental physics. The interactions between Pluto, Neptune and other planets are not random, but affect the fundamental laws of life. By studying these interactions, humans can gain a deeper understanding of the fundamental forces of the universe and how the universe is created. Many small and icy bodies, one of the largest members of the Kuiper belt, Pluto's orbit takes it deep into this region, where it interacts with other objects in the Kuiper belt. Pluto's orbit. These disturbances can cause orbital drift, adding complexity to the complex dynamics of Pluto's orbit around the Sun. Understanding these interactions is critical to obtaining a complete picture of Pluto's orbital mechanics. In addition to interacting with the Kuiper belt, Pluto is influenced by its larger moon, Charon. The Pluto-Charon system is unique in that the center of mass, of both bodies lies outside Pluto. This mutual orbit creates a magnetic interaction between Pluto and Charon, affecting Pluto's orbit and interactions with other planets. Pluto also has 5 small moons, Styx, Nix, Cerberus, Hydra, and a recently discovered 5th moon. Although these moons exert little influence on Pluto, their presence adds layers of complexity to the dynamics of the Pluto system. Studying these moons provides a better understanding of how smaller bodies in the sky interact with their larger counterparts. One of the main tools for understanding Pluto's orbit is an astronomical observatory. Using ground-based and space-based telescopes, scientists can track Pluto's position with great precision. For example, Hubble Space Telescope observations have provided valuable data on Pluto's orbit and its interactions with other bodies in the solar system. This observational data is needed to refine models of Pluto's orbital behavior and predict its future locations. The continued study of Pluto's orbit through astronomical observation is helping scientists better understand the complex atmospheric interactions in the solar system. In addition to observational data, numerical simulations play an important role in the study of Pluto's orbit. Astronomers use these simulations to explore the different conditions and consequences of Pluto's interactions with other celestial bodies. By combining many factors, including the effects of all known planets and large moons, as well as interference from other Kuiper belt objects, scientists can predict changes future in the orbit of Pluto.